Is your kitchen stove actually a miniature version of space rockets? Both use controlled fire. Which mystery is stranger? Comment your thoughts. You mix gas and air to create a steady, hot flame. Rockets simply scale this process up to massive, explosive proportions. A nozzle shapes that expanding gas into pure, directional thrust. High pressure inside forces the exhaust out at incredible speeds. It is just converting chemical energy into motion, very efficiently. The secret is how we manage heat without melting everything. Rockets use their own fuel to cool the engine walls. Nature obeys the same laws in your kitchen and space. Your kitchen stove relies on steady, controlled chemical combustion reactions. Atoms rearrange themselves, releasing energy as heat and bright light. Your burner pulls oxygen from air to keep flames alive. Rockets cannot rely on atmospheric oxygen in the deep vacuum. Engineers pack liquid oxygen tanks to feed the hungry fire. Pumps push fuel faster than a stove could ever manage. A rocket nozzle shapes that energy into pure directional thrust. Metals glow cherry red, dancing near their ultimate melting point. Cold fuel circulates through engine walls to prevent total meltdown. It is the same basic chemistry your kitchen stove uses. Your kitchen burner mixes fuel and air for steady heat. Rockets perform this exact dance, but at a massive scale. Stoves rely on house pressure, while rockets use powerful pumps. Too much fuel creates soot instead of pure clean energy. Hot gas molecules push against everything to find more space. A stove disperses heat, while a nozzle focuses exhaust speed. Choke the flow to accelerate gases to supersonic exit speeds. Rockets use fuel as coolant before burning it for thrust. Both systems lose precious energy to simple radiant heat loss. Nature follows the same rules in kitchens and deep space. Your stove mixes fuel and air for a steady flame. Rockets demand precise ratios to achieve maximum combustion efficiency today. High-pressure pumps force fuel into the combustion chamber forcefully. Expanding gases push against the nozzle to create immense thrust. A shaped nozzle accelerates exhaust gases to supersonic speeds instantly. Regenerative cooling cycles fuel around the nozzle to prevent melting. Oscillating pressure waves can destroy an engine in mere milliseconds. Your stove avoids instability because its pressure is extremely low. Rockets scale this simple process to generate millions of pounds. Building reliable high-pressure systems remains a complex engineering challenge. Your kitchen burner regulates gas flow just like rocket injectors. Both systems require precise mixing to maintain a stable fire. Inside the burner, gas molecules ignite into a controlled explosion. Heat forces gas to expand rapidly, creating powerful directional pressure. Rockets use a nozzle to focus that heat into thrust. Stoves melt if they get too hot, just like rockets. Rockets circulate cold fuel around the chamber to stay cool. It is all about managing energy flow with extreme precision. Your morning coffee uses the same physics as orbital insertion. Wait until you see how we ignite these massive engines. Your gas stove regulates fuel flow just like rocket injectors. Tiny holes atomize the fuel for a perfect burn rate. Too much air kills the flame, just like in rockets. Rapid expansion of gases creates the force we call thrust. Your stovetop is essentially a miniature, open-air rocket combustion chamber. High pressure inside pushes gas out at incredible sonic speeds. Rockets use shaped nozzles to focus this energy into motion. But wait, your stove lacks one vital component for orbit. Rockets must carry their own oxygen to burn in space. A rocket engine burns millions of times more fuel daily. Your gas stove burns fuel efficiently with the right air. A rocket engine requires precise mixing of fuel and oxygen. Too much fuel makes the flame yellow and very inefficient. Rockets simply scale this process to create massive controlled pressure. Stoves dissipate heat, while rockets channel it through narrow nozzles. A nozzle accelerates hot gas into a powerful supersonic stream. Fast-moving molecules push against the engine to create thrust. The laws of thermodynamics apply equally to pans and rockets. Rockets just do it much louder and with more danger. Soon we will see how pumps move this volatile mixture. Your stove regulates gas flow just like a rocket engine. Perfect combustion requires the exact right mix of fuel-oxygen. Hot gas expands rapidly to create pushing force against surfaces. A stove lacks a nozzle, wasting energy in every direction. If you enjoy this insight, please hit that like button. Rockets use convergent nozzle to accelerate exhaust to supersonic speeds. Hit the subscribe button and press the bell icon to get updates. Stoves lack the massive pressure needed for actual orbital flight. Rockets use liquid fuel to pack more energy per volume. The fundamental physics of fire remains identical regardless of scale. High-pressure gas naturally rushes toward areas of lower pressure. Your stove releases gas through tiny holes to create heat. Rocket engines use thousands of similar holes called injector plates. They precisely mix fuel and oxidizer for a perfect burn. This mixture ignites inside a chamber built for extreme heat. Burning gas expands rapidly, seeking an exit from the chamber. A shaped nozzle forces this expanding gas to supersonic speed. The rocket pushes gas back, so gas pushes rocket forward. Stove flames are orange, but rocket exhaust is often blue. Blue means the combustion is cleaner and much more efficient. Your kitchen stove relies on mixing fuel with surrounding air. Stoves pull oxygen from the room to sustain their flame. Rockets cannot breathe because space lacks any available oxygen supply. Engineers solve this by carrying tanks of liquid oxygen aloft. Just like your dial, rockets precisely regulate their fuel flow. High-pressure pumps replace the simple flow of your kitchen. Both systems convert chemical energy into intense, focused thermal heat. The secret isn't the size, but the speed of reaction. Rockets accelerate exhaust gas to supersonic speeds for maximum thrust. You are witnessing the same basic physics on a scale. Your gas stove releases fuel through tiny, precise nozzle holes. Rocket engines use an injector plate to spray fuel similarly. Both systems require mixing fuel with oxygen for efficient burning. Engineers calculate the exact ratio for a clean, hot flame. But rockets must force this mixture under immense, crushing pressure. Turbopumps replace the simple valve found on your kitchen range. A stove flame is steady, but rocket flames are violent. Wait for the nozzle shape to dictate the engine's thrust. Expanding gases accelerate past the speed of sound behind you. It is just a very loud, very angry kitchen stove. Your stove mixes gas and air to create controlled heat. Rocket engines use that exact same principle, but much faster. Valves regulate fuel flow to ensure a steady, hot burn. Expanding gases push against the engine wall to generate thrust. Your stove is tiny, but rockets require massive pump systems. These pumps force fuel into the chamber at incredible speeds. Regenerative cooling uses cold fuel to keep engines from melting. The physics of your kitchen stove actually masters orbital flight. Nature follows the same rules, whether cooking food or rockets. The facts remain, and the search for truth continues.